So let's talk about if you're an intern and you need to bring the office some Popeyes chicken sandwiches, and you need to know how much 15 sandwiches are going to weigh because you had a back injury or something. I don't know. Sounds like an old man idea. But anyway, hopefully you're familiar that if you had to weigh how much the chicken sandwich weighs, even though there's one chicken and two buns and two pickles, um, just because there's more buns or more pickles doesn't mean they weigh more, right? The chicken's going to weigh the most, even though there's only one piece. And that should not surprise you. And basically, that's how you would figure out how the whole thing weighs, right? If you know the mass of the buns and the mass of the pickles and the mass of the chicken, if you add them all up, then you would have the mass of the sandwich. Well, that's what we're doing with formula mass. Formula mass is the sum of the atomic weights of a molecule or a formula unit. So this is basically talking about atomic compounds. And there's my picture of formula at mass, which would kill at Gibbons. Anyway, all right, so let's talk about what a formula unit is. Remember, I've tried to discuss this for years. Uh, if you have magnets, and these are magnetic spheres, and they stick together, right? And there's no stopping them sticking together. So even if the smallest unit of repeating is this Cl and Na, it's just going to keep going on and on and on forever and ever because things just are going to want to keep sticking and sticking and sticking. So we call that the formula unit of the lattice, right? So this is sort of a lattice, and that's just the repeating formula unit. So this is the formula unit. The point is, it's an atomic level thing. A molecule, on the other hand, sort of has a distinct beginning and a distinct end. There is no connecting them, as you can see here, right? You can sort of draw a line between them. They're not stuck together. And when we played with this FET with water, the water molecules are not connected like we saw here, where these things are all kind of connected. Of course, that wasn't a formula unit there, but it would be like that as a solid, and the solid water would not necessarily be bonded together. They would just be attracted to one another in a solid. But anyway, the point being here, you have a beginning, you have an end, right? Each of these is its own thing, and we call that a molecule, but still it's an atomic scale. So in both of these situations, we're talking about atoms, atomic level kind of thing. And so therefore, they're very, very, very small. And because they're so small, guess what we're going to need again? Avogadro's number. So it actually turns out you need a billion molecules to hit your nose before you start smelling something. So consider some of the things you've smelled and how that means there have been a billion molecules in your nose for your nose to even register that smell. Um, so obviously molecules are very small. You don't necessarily even see them going in your nose, but that's how many things need to affect your nose's receptors before they start telling your brain, "Hey, you know what? I think you smell dog poop." So one molecule of water, two hydrogens and an oxygen, is going to weigh a total of hydrogen is one, and hydrogen again is one, and oxygen is 16. So altogether, that weighs 18 atomic mass units. All right. But 1 mole of hydrogen of water molecules is going to equal 1.01 times 1.01 and 16 still. So you're going to get 18.02 grams. All right. So just like we were doing yesterday with the other thing, 1 mole of water molecules is also going to contain 6.02 times 10 to the 23rd molecules. Now that I think about it, that probably should have been up there. But anyway, that's why we practice. All right, moving on. So when we're talking about molecules, we're talking about these little itty bitty, right? Little individual atoms connected together. When we're talking about a mole, we're talking about enough to use in a lab, right? A laboratory size sample, which I'm circling with an eraser. A laboratory size sample of water, 18 grams of water is what that is. All right. So what's the molar mass of C4H10? So if you go to the periodic table, I should put a periodic table closer than this, but bear with me. All right, so C4, so you got 4 of these and 10 of those. Okay, so 12.01 and 1.008. So honestly, for all intent and purposes, hydrogen's 1. That's what we do. That won't burn me later. All right, so carbon, there's 4 carbons. So the number of atoms is 4. And then the mass of those atoms is 12.01. So that's 48.04, right? The hydrogen, there are 10 atoms. Each one weighs 1.0. So we're going to go with a weight of 10. And so when you add that up, you get 58.04 grams. So the molar mass of this is 58.04 grams. All right, C12H22O11. Let's break that one down. So carbon again, number of atoms of carbon in this is the 12. And each one has a mass, somewhat confusingly, of 12. So that's 144.12, I think. Then the hydrogens, there are 22 of those. Each one of those weighs 1. So we're going to call that 22. And then the oxygens, let's do that red in deference to Dr. Hart. So oxygen, there are 11 of those. Each one weighs 16. So 11 times 16 is, I can't do that one in my head, unfortunately, 176. And then we're going to add all those up. So 176 plus 22 plus 144.12 gives us a grand total 342.12 grams. So that's how many grams 1 mole of this weighs, 342.12 grams. All right. So this is kind of easy, I would hope. Remember, when there's parentheses, we distribute, right? So this is a distribution of this 3. So it's 3 times 4 and 3 times the 1 on sulfur. So iron, number of atoms is 2. And each iron weighs 55.54. Let's find out. Iron, 55.84. Not even close. And while we're here, let's get sulfur. Sulfur is 32 and the oxygen 16. Okay, so 55.84. 55.84. 55.84 is the mass of each one. So you're going to multiply that. 111.68. And then the sulfur distributed that 3. So there's 3 atoms and each one weighs 32.06. So 32.06 times 3 is 96.18. And then the oxygen, there are 12 of those, 3 times 4, and each one weighs 16. So 12 times 16 is 192. And then we're going to add all those up. So plus 96.18 and 111.68. And we get 399.86. And that's what 1 mole of iron sulfate. I think that's iron 3 sulfate, if I had a, not really thinking. Let me write that first. Yeah, iron 3 sulfate. All right, so calcium acetate, same thing. Remember, this is going to distribute. So we're distributing this 2. So 2 times 2, 2 times 3, 2 times 2. So the calcium is, there's 1 of those. And each one has a mass of, I believe, about 40. Let's check out calcium real quick. Close your eyes if you get car sick. Calcium, 40.0708. So let's go with 40.08. Should have looked at other things, but 40.08. Actually, I know the rest of them, right? Carbon. So 2 times 2, there's 4 carbons. Each one weighs 12. Um, hydrogen, 3 times 2 is 6. Each one of those weighs 1. And oxygen, each one of those weigh 2 times 2 is 4, and each one of those weighs 16. Dr. Hart's unhappy with me for not making it red. But anyway, all right. So, well, I don't even need to calculate for that one. That's 40.08. Lovely how your pen does that. 12 times 4 is 48. 1 times 6 is 6. And 4 times 16 is 64. So we're going to add all those up. And we're going to get 40.08 plus 48 plus 6 plus 64 is 158.08. So this is weighs 158.08 grams. All right. So that should not, and that's in 1 mole, right? This equals 1 mole. This equals 1 mole, right? That's what we're doing here. This equals 1 mole. This equals 1 mole. All right. So basically, this is everything we were doing yesterday, except now we're going to make this a little more work. So 28 grams of carbon dioxide is how many moles? Well, then we got to figure out carbon, which has in carbon dioxide 1 atom with a mass of 12. And oxygen, here we go, Dr. Hart. I'll hook you up here. There's 2 of those. Each one has a mass of 16. So we got 12 plus 32 is 44 grams per mole. So if we have 28 grams and each one weighs 44 grams in 1 mole. So again, this came from the periodic table. Then we're going to divide 28 by 44 to figure out how many moles we got, and we get 0.6363. So the answer is 0.6336 moles. So hopefully that's not shocking how we're doing this. This is just like we were doing yesterday. So C6H12O6, again, we got to make our little chart. So carbon has 6 atoms. Each one has a mass of 12. So that's 72. Hydrogen, there are 12 atoms. Each one has a mass of 1. That's 12. And oxygen, there are 6. Each one has a mass of 16. 96. And you add all those up, and you should get 180, I believe. 72 plus 12 plus 96. 180. Look at that. So that's how many grams there are in 1 mole. So if we have 1.50 moles, then we want 1 mole from the periodic table has the 180 grams. Moles will cancel. 1.5 times 180 is 270 grams. Okay, so I don't think this is shocking. Same highway that we were using yesterday, grams to moles, right? The periodic table turns grams into moles, and the periodic table turns moles into grams. Sing the song with me. And we use Avogadro's number when we're using the word atoms or molecules or formula units. So anything that's a molecular scale, we need to use 6.02 times 10 to the 23rd. All right, so if we have this number of molecules, right, we're going to need 6.02 times 10 to the 23rd. So we're going to start with that 5.87 times 10 to the 22nd molecules. And molecules will need to go to moles. And moles is always 1 mole, regardless if it's from Avogadro or the periodic table. So 6.02 times 10 to the 23rd of those. That's moles, but we need grams. We're not there yet. We need to go grams. So this is a second step. And for every 1 mole water, so water is H2O. So that's hydrogen, 2 atoms of hydrogen. Each one has a mass of 1. And oxygen, I might as well switch because I learned in the last one. And each one has a mass of 16. So 16 plus 2 is a total of 18 grams. So that's 18 grams in 1 mole. So you divide or you multiply 5.87 times 10 to the 22nd times 18 and divide that number by 6.02 times 10 to the 23rd. And you should get 1.75 grams. All right. So even though you have all those molecules, it only weighs 1.75 grams, just about 2 milliliters. So not much of anything there. All right, 122 grams of NaCl to formula units. So we're going to start this one with 122 grams of NaCl. So we got to go to the periodic table and figure that one out. So Na, there's one atom. Oops, atoms. There's one of those, and the mass of each one is 22.9 or 23, basically. Just trust me on this. I'm going to use my own periodic table rather than get you car sick again. So sodium is 22.98. So yeah, basically 23. 23, and chlorine is there's one of those, and that's 35.45. So 23 plus 35.45 is 58.45. So I don't round many of them. That maybe you should always bring as many as you want here. This is just because I'm doing it by memory, but you always want to bring one decimal place if you can, um, and then you'll be fine for the rest of the semester. But if you want to do two decimal places or everything you see, that's not a problem. More accurate results are good. But this is a little bit of laziness and a little bit of being a chemist for my whole life, so I kind of know some of these things. So I kind of know where you can cut corners, but you don't want to cut corners at the point fours and whatnot. You want to not round those up. Anyway, 58.45 grams, and that is in 1 mole. This was looking for formula units though, so we don't want to stop there. We want to keep going, and formula units in 1 mole are 6.02 times 10 to the 23rd, right? That'll get rid of moles, that'll get rid of grams, and then 6.02 times 10 to the 23rd. Formula units. So there you go. 122 times 6.02 times 10 to the 23rd divided by 58.45. 1.26 times 10 to the 24th. 1.26 times 10 to the 24th formula units. So this shouldn't knock you out.